Okay, so here we're kind of looking at an extension of the previous problem I just talked about when we talked about the stoichiometry involved with these delta H's. And so whenever I kind of introduced those concepts, I made sure to mention the fact that whenever you manipulate anything that has to do with the equation, you have to do almost exactly, no, not almost, you have to do the same thing with the delta H's. And so in this particular problem, I give you three equations along with their delta H's. And so this equation in red is our target equation, or it's the equation that we're actually looking at, that we do not have a delta H here. And so the great thing about this, in addition to Hess's law, is Hess's law states it doesn't matter how you get to the final result, as long as everything kind of lines up, and as long as you know individual pieces, you can add up like all the individual pieces to give you the overall sum. Or essentially what I'm trying to state is if you can figure out how to put all three of these equations together to give you this overall equation, you can do the exact same thing and add up all three of their delta H's to give you the overall delta H. And so the main issue that comes along with this is a lot of you seem to over panic and analyze these things. And so all you really need to do, and again, not saying it's this simple, but trying to like less complicate things, is you just need to make sure all your reactants and your products are on the correct side. And what I mean by that is go through each one of these individual reactions and make sure that your products are products and your reactants are reactants and not the other way around. In addition to that, you need to make sure that the coefficients for those reactants and products are the same as well. And so if we kind of start off with reaction number one, or this carbon plus your O2 will give you CO2. And so if you kind of take a look at the red equation, our target equation, you notice that carbon is not there. And so for right now, let's just ignore carbon and come back to it. And so oxygen in this case is a reactant in our equation one, and it's a reactant in our target equation as well. So we're good on that account. Same deal with our CO2. In our equation one, our CO2 is going to be our product. In our target equation, our CO2 is a product as well. And so everything in reaction one is good to go for now. So let's take a look at reaction two. And so in equation two, I have sulfur plus our O2 will produce our SO2. And so now taking a look at this, similar to the reaction one, sulfur is in our equation two, but it's nowhere inside of our target equation. So don't panic yet, just hold it off until the end and hopefully everything will work itself out. Our oxygen, again, is a reactant in our equation 2, and it's a reactant in our red target equation as well. And so the position of our oxygen is okay. Same deal with our SO2. Our SO2 is a product here, it's an SO2 is our product there as well. But one thing we do have to kind of take a look at here is we have one SO2 in our equation 2. We have two SO2s in our target equation. And so the way that we can fix that, as we've done in the past, is if we need more than our equation is giving us, we have to manipulate the entire equation. And so if we need two SO2s, we need to multiply all of this by 2, or again, have our 2 over S's, 2 over O2s, and 2 over SO2s. But because we did that, because we made a change to our chemical reaction, we need to make the same change apply in our delta H. And so our delta H in this situation must be multiplied by 2 as well. And so once we do that, then we have our 2 SO2s, we're good there. We have our 2 O2s, and we have our O2 from previous one, and as you'll see, that will work out to our advantages as well. So let's look at step 3. And so with our reaction 3, we have carbon, which as I kind of mentioned with step 1, just kind of ignore for now. Same deal with the sulfurs, we'll kind of hopefully work that all out in the end. So let's take a look at our CS2, because that's the only thing that really exists in our target equation here. And so the CS2 in our equation 3 is a product, but our CS2 in our target equation is a reactant. And so what we need to do here is rewrite this equation, but we need to make sure that it is rewritten in a correct format according to what we are actually looking here. And so because we need to make sure that our CS2 is a reactant, we need to take this entire equation and flip it on the other side. And so if we kind of rewrite this equation here, we are going to make our CS2 a reactant and the other two things a product. So now our CS2 liquid is our reactant, and that is going to break up into our carbon solid, plus our 2 sulfurs. But because we flipped that chemical reaction, this delta H right here was going to again be for the way that it was written. But since we flipped it around, we need to again change the sign of our delta H, because the way we written that positive 87.9 was telling us it's an endothermic reaction. But as soon as we flip this entire chemical reaction around, our endothermic reaction is now an exothermic reaction. And so we have to make sure to indicate that by changing the sign of our delta H. And so now if we kind of go through and take all of our reactants or products here and we add all 3 of these equations, you would end up with 1 carbon, 1 oxygen, 2 sulfurs, 2 oxygens, and the CS2 on the reactant side. And so here again, your 1 O2 and your 2 O2s will give you 3 O2s. Very similarly, on the product side, you'll have CO2 plus your 2 SO2s to give you, or plus carbons plus 2 sulfurs. And so to write all this out, you would again have I'm going to ignore all of the states of matter because they haven't changed, but a carbon plus an O2 plus 2 sulfurs plus a 2 O2s plus the CS2. And again, this will all give you your CO2 plus your 2 SO2s plus your carbon plus 2 S's. And so, main reason why I told you to ignore your carbons and your sulfurs, because hopefully in the long run those will cancel out. And as you can see here, we have a carbon here that becomes a carbon there, and so we can cancel those out because they did nothing. Same deal with our sulfurs here and our sulfurs there. They did nothing as well, so we can cancel those out. And so in the long run, writing everything out here, we have our O2 plus our 2 O2s, and so we end up with 3 O2s. We have our CS2 is still going to be sitting there, and so we have our CS2. On product side, we have a CO2 and 2 SO2s, and so CO2 plus 2 SO2s. So we kind of compare these two, 3 O2s, 3 O2s, CS2, CS2, CO2, CO2, 2 SO2s, 2 SO2s. The way that we ended up with this equation is we added that value plus 2 times that value plus the negative of that value, or it was negative 393.5 plus our negative, I forgot how to do math here, but it's 593.6, and then plus our negative 87.9. And so all of these are added together, and I end up with a negative 1075 kilojoules per mole. And so one thing you have to remember here is do not freak out. Just treat these chemical reactions the same way we've kind of done this stuff in the past when we were talking about the sequence reactions. Just need to make sure that if you change anything inside your chemical reaction, you have to change the exact same thing in your delta H's to signify that you are, again, changing the actual reaction. So therefore, you're going to change the amount of energy required or the amount of energy released.